Hello everyone, in this video we're going to talk about something you should not do, and that is reviving a lithium-ion battery pack. Now if you're not a regular viewer of mine, which may be the case if I have referenced this video in another platform, I make videos predominantly currently about Onewheels, although that is slowly shifting, but I run an electric skateboard repair shop where I fix boards and, in many cases as a result of that, build custom lithium-ion batteries. And to specify further, my area of current expertise is lithium-ion battery packs constructed of things like these cylindrical lithium-ion cells. So that is what I'm talking about in this video, and that is the context that I wanted to offer. This battery is being built, or well, it's been built, it's being finished to replace this one. And this one has been drained essentially flat. It is dead. Now the maximum voltage for this pack when it is full is 29.4 volts. Empty is around 19 volts, and this pack is currently reading at about 9 volts total, which means that this is well below empty. This thing is considered dead, and it has been condemned and taken out of use. Now, the removal of a lithium-ion battery pack from use is not a very common scenario. It's always an unfortunate one because when you have to replace an entire battery pack, it's usually a very costly thing. And I brought some out to the floor just for display. It is an old Cali battery, and this was part of an overall custom rework of a board. Video on this is coming as well. There is a now defunct Onewheel pint mod battery. That's an old Evolve prismatic pack that used to exist inside of a Bamboo GT, and that's another brick pack that has since been condemned and taken out of use. There are a couple others, but they are sealed away in storage, and some of these may be featured in an upcoming video where I test the Nobleman Tech fire bag, and some of these might feature in that scenario. But there are occasions where you simply have to take a battery pack out of use because it is no longer safe to use. Now, I will link to another video that I made previously on charging. It was aimed particularly at charging Onewheels, but the second half of that video was pertinent to charging any kind of lithium-ion battery in a personal electric vehicle. And so to set a bit more of context, this right here is a cylindrical lithium-ion cell. And these packs that I deal with are comprised of many of these connected in series, connected in parallel to form the necessary voltage and capacity that is needed for any particular device. Now, the voltage range of a cylindrical lithium-ion cell is from, at the top, meaning full, 4.2 volts, to the bottom, anywhere from 2.5 to 2.7 to 2.8 volts, generally speaking. Now, if the voltage of a cell falls outside of that range, it can become dangerous. Overcharging a lithium-ion cell does damage it, and continuing to do so can lead to venting or some kind of catastrophic failure. Undercharging, or rather draining a lithium-ion cell well past the point that it's considered empty, is not necessarily a dangerous thing in and of itself, but the danger comes when, after that has happened, you attempt to recharge it after it has been sitting for a while in its totally flat, dead state. And so back to this pack that we are going to attempt to revive/recharge using the power supply. I'm going to set up the camera, set this thing to start charging, and explain what I'm doing and also why you should not attempt to do this. Now, I was compelled to make this video after yesterday a gentleman brought in an electric unicycle to have its battery checked out, and the particulars of that situation aren't entirely relevant, but the situation itself is an unfortunately common one. The device was left on for a period of time after the battery was already very low, and so the constant slow drain of the device, or rather of the battery from the device, led to it dropping well below its empty threshold. And the behavior of any particular lithium-ion battery pack when it is drained that low can vary depending on how it's built, the cells that are used inside of it, and the way it was drained or discharged down to that point. But the scenario often ends up being a common one where there is simply not enough energy left in the pack to sustain a current draw from a high-powered device like a personal electric vehicle. And so in the case of this battery, we have something that has not only been drained to flat dead, it is currently at about 9 volts. Previously it was at 7. I did pump a little bit of current through this just to make sure that it wouldn't warm up and or blow up. Now this particular battery had been drained way down below its empty voltage to essentially dead flat, 7 volts total, even though empty for this battery pack should be about 19 volts, so it's well below empty. And it has sat there for an extended period of time. Now, you'll read different time frames for how long a battery can be depleted entirely before it's no longer safe to revive it or try to recover it. And the most common one I see is if it's been left at too low a voltage for over a week, that is very much no longer safe to try to revive or recover. I have my own personal thresholds. Usually if a battery is drained severely and has been sitting at that too low a voltage for more than a couple of days, I will personally consider that thing unsafe, and I will recommend that the end user take it out of use and replacing the entire battery. Now, some battery packs have two distinct circuits for charging and discharging. Some have a common circuit that is used for both charging and discharging, and that's governed by the BMS. And in this particular case, the BMS will no longer allow a charging of the battery because the voltage is too low. And so what has to happen is this needs to be charged and brought back up to its regular assumed voltage through the main terminals of the battery. Now this discharge circuit is direct, so that means that this is connected to the main terminals, the positive and negative terminals of the battery pack. So this particular circuit runs through the BMS, this does not. So we will have to apply a voltage to run current through the main terminals of the pack. Now that, if you're going to do it, which you should not, and we're going to talk about why you should not while this is starting to charge, but you're going to have to do that in order to get the voltages of each cell up enough for the BMS to register. Now, if you are going to do this for academic purposes only, because you should not do this under any circumstances, because, to be perfectly honest, this is not safe. This has been dead for a very long time, so doing this is not safe. If we are going to do this just to observe the effects of the battery under such a recovery process, here is how we would do it. So we have the power supply set to a voltage that is higher than this current pack. Now, I am not going to bother setting the power supply to the total high full voltage of this battery because we are not going to charge it through the main terminals the entire way. We are going to charge it roughly about halfway at a very, very slow charge rate. So if you're not entirely versed with this and you see your device has a charger that outputs 3 amps, 6 amps, 10 amps, we are going far, far, far below that. This is currently set to about 100 milliamps, so that's 0.1 amps, and this is a 4P pack. So this is about 25 milliamps per cell. And even that is a pretty fast charge rate for recovering or reviving a dead lithium-ion battery pack. Quite frankly, it should probably be closer to half that, like 10 milliamps per cell. But this is for display academic purposes only, so that way we can observe the behavior of the battery under such a condition. So we have our charge adapter going into the main terminals. And actually, before we even do that, let's use our digital multimeter to check the voltage of the pack. The power supply will read it as well. However, this is currently reading at 8.92 volts, which means that it has dropped. It was currently, the last time I read it about half an hour ago, at 9.2-ish volts. So it has dropped, which is an indication that this is not holding on to the voltage that we need it to do, which is yet another indication of why we should not try or attempt to recover dead lithium-ion batteries. But again, this is merely for academic purposes, and we are going to attempt to recover this very, very slowly while discussing why no one should do that. So now we have the battery hooked up to the power supply, and this has a battery charge function, which we are using here. And again, this is going directly into the terminals, and so there is no BMS being dealt with here. This is direct, which also is something that is often required in the event of recovering or restoring a battery or whatever you want to call it. And it's another reason why this is so dangerous to attempt and why you should not. So the power supply does give us some information that it reads from the battery. It gives us the voltage that it detects, so 8.91 volts. And then since it's on the battery charge function, it will tell us how much energy and capacity we have put into the battery. So we set the voltage to 20 volts. That is the voltage that is going to be applied to the battery, and it is limited to 0.04 amps. So I actually lowered it, and we are going to put about 10 milliamps of current. That is going to be our limit in this whole entire scenario. And so now that it's hooked up, we have an indication that it does detect that it is connected to a battery, and we are going to turn it on. It clicks on, and you'll notice the voltage rise relatively quickly. And that is because at that low a voltage, there simply is just not a lot of energy left in the cell. Now, while this voltage very slowly climbs, well, actually very quickly climbs because we are reaching 20 volts relatively quickly, I believe once it starts to near about 18 or so volts, this will slow, because it is that point when you reach around 2.8 volts-ish or 2.5 volts per cell that most of the energy accumulation begins to happen in the cell. So down at this voltage range, the cells don't have a lot of stored energy. It's why a cell can drop from 2.8 all the way down to 1 volt or less very, very quickly with very little drain from a device. It's why it makes this sort of scenario, unfortunately, more common than we would like it to be. Now, why is this such a dangerous thing to try to do? Well, it really comes down to what is happening chemically inside the cells when they are discharged so far. So you have a normal operating voltage range from, say, 2.8 to 4.2, empty to full. Below that range, the chemical concentrations in the electrolyte are beyond what the cell is designed to deal with. So what ends up happening is that the metal from the negative terminal or the negative pole of the cell begins to dissolve into the electrolyte. Within the cells, these is actual liquid electrolyte. And the negative pole, which is actually the entire can of the cell, but we assume it to be right there, there is metal at that terminal. That metal begins to dissolve into the electrolyte of the cell and floats around in that liquid. If it sits that way for too long, more and more of that metal begins to dissolve into the electrolyte, and that begins to set up a potential hazard. The potential hazard is that when you now apply a voltage to restore the charge to the battery, that dissolved metal begins to replate itself. Now, the issue is that we cannot control where it replates itself. It can replate itself nicely on the terminal. It can form in the electrolyte, just floating around. And these dendrites that form are spiky metallic structures. They can then lead to internal short circuits of the battery if they pierce the separator. They can also just damage the terminal, the negative pole of the battery, because when dendrites start to form at the pole, they then compromise the cell's ability to function as it used to in terms of electron transfer from the pole to the electrolyte through the separator, etc., etc., etc. I will link some literature on dendrite formation in the description below. It's interesting stuff to read about, but the formation of dendrites when recharging a cell that has been left to sit at dead flat for so long is one of the primary risks that one runs into when you attempt to recover it. Now, what does this even mean? What does this mean in practice? Well, in the luckiest of circumstances, nothing bad actually happens, which is what I am hoping for this battery right here. I'm hoping to be able to bring it up near to full voltage and nothing will happen to it. However, since no one can really control where dendrites form, how much they form, or if they form at all in a scenario like this, there is just now the situation where you don't know what is going on inside the battery. One can have a battery sit at below empty, at totally flat dead, for an entire week. You can recover it and then charge it through the BMS, have all the cells balanced and everything is fine, and it can work perfectly like that for a month or two. And then one day you go to charge it again, there's an internal short somewhere in a cell in the pack due to the damage that was incurred when it was totally undercharged, and now you have a catastrophic failure in the middle of a large battery that you cannot get to, and so the entire battery incurs a catastrophic failure and you're left to deal with that, however that may manifest. Am I saying that if you drain a battery to entirely empty and flat, that if you attempt to recover it, it will burn your house down? I don't know. I don't know. Because once you keep a battery outside of the spec that the manufacturer has designed into said cells, you are just rolling dice. You're rolling dice for every possible scenario, and that is actually where the danger lies, is in not knowing. No one knows when the pack will fail, if the pack will fail, what form that failure will take. And so that is why if you have a device with a very large, honestly any size, but especially a very large lithium-ion battery, and it has been drained, you left it on or you left it there near dead over a summer or a winter and it won't turn on, and you look at it and it's reading 1 volt, 2 volts for the whole entire pack, something like that. If it is flat dead, do not try to recover it. Do not ask anyone to try to recover it. And if you bring it to someone and you honestly tell them what the scenario is and they try to recover it, I would question their judgment. And so that's really the crux of this entire thing. You know, so forgive me for making you stare at a power supply charging a dead battery in hopes that nothing catastrophic happens, because I realize it doesn't make for very entertaining viewing, but there will be very entertaining, fiery, catastrophic viewing in a future video when we test the fire bag. But this is all to say that should someone recommend to you, if you have a dead battery, totally flat, if they recommend to you, oh, I think you can recover it, you should try to recover it, you can charge it outside of the BMS so that way you can revive it, just don't do it. Your personal safety is not worth it. The risk of property damage is not worth it, because when you do things like that, move the camera, when you do things like that, just for the sake of saving X amount of dollars to recover a battery, the risk to me is simply not worth it. Yes, in many cases, especially in the event of you have a very large electric skateboard, you have a Onewheel, you have an electric unicycle, whatever the case may be, a battery replacement may be prohibitively expensive. Thousands of dollars for some of the very large batteries. You know, this is a relatively inexpensive battery pack, but if you have something that has 144 cells in it, that's not cheap to replace, I understand that. However, what is the risk actually worth it to you? After the battery's been damaged from sitting dead flat for X amount of days, what is the risk? What are you actually going to incur from attempting to save something? Now, this is still, and I feel very fortunate to be in a privileged spot to say this, just a material thing. And the risk that this can present from wanting to charge it, revive it, and put it back into use is far too great. I'm in a setup where I have fire suppression in the shop. I have access to the street in the event that a catastrophic failure does happen of any product or any item in my shop. I can deal with it, and there are practices in place to deal with that. That's not the case if someone is housing PEVs in an apartment, if they are housing lots of batteries in a building or a residential area without an escape plan or a fallback plan or something like that. And so doing this is something that you should not do. I really don't think anyone should recommend anyone else do. If your battery has been sitting flat, condemn it, recycle it if you can, and begin the very painful process of trying to figure out how to replace it and proceed from that point. Reviving batteries and recovering lithium-ion batteries is something, in my opinion, you should never do. It is not worth the risk. Thank you for watching. I hope this was helpful. I don't know if it was entertaining or not. If this is the kind of content that you like, there is more of it coming, and I honestly appreciate your viewership. Take care of yourselves.